Welcome to Understanding Climate with Professor Monks. Today's topic is the greenhouse effect. We've learned that the largest components of our atmosphere are nitrogen, oxygen, and argon, while greenhouse gases, sometimes abbreviated GHGs, like carbon dioxide, methane, and water vapor, make up only a fraction of a percent. That's a very good thing. If we had less greenhouse gases, we'd all freeze. If we had more, we might end up like Venus, where the atmosphere is 96.5% carbon dioxide and surface temperatures average 462 degrees Celsius. But what makes a gas like carbon dioxide function as a greenhouse gas, while others, like nitrogen, don't? You may have noticed that the non-greenhouse gases all have very simple chemical formulas. An oxygen molecule is just two oxygen atoms stuck together, and nitrogen is the same way. Argon just exists as single argon atoms. But greenhouse gases have more complex molecules. A more complex molecule has more ways that it can bend and twist. You can visualize that if you imagine the bonds holding the atoms in a molecule together as tiny springs that can be stretched, squished, and bent. Consider an oxygen molecule. Its two oxygen atoms can stretch apart or squish together, but that's about it. That's a symmetrical motion, so it doesn't cause ripples in the electromagnetic field. Now consider a molecule of carbon dioxide. It can stretch and squish symmetrically like oxygen, but it also has two other types of movement it can make. It can stretch and squish asymmetrically, with the carbon atom in the middle getting closer to one oxygen than to the other. And it can bend into a V shape, with the two oxygens coming together on one side. Because the atoms have different electrical charges, these asymmetrical movements create ripples in the electromagnetic field at a certain frequency. The more different ways a molecule can move, the more different wavelengths of radiation it can absorb and emit. Here we see the wavelengths of energy that different greenhouse gases can absorb and emit. You'll see that each gas has certain wavelengths it likes and others that it ignores, based on the specific structure of its molecules. CO2, for example, really likes energy with a wavelength of about 15 micrometers. The sun's shortwave radiation largely passes through the atmosphere unimpeded to be absorbed by the Earth's surface. The Earth radiates energy back out at longer wavelengths. Some of these wavelengths are absorbed by greenhouse gases. Other wavelengths aren't absorbed by greenhouse gases that are common on Earth, so those wavelengths pass through into space. When greenhouse gases absorb radiation, they then re-radiate it back out. Greenhouse gases aren't a total lid on the Earth trapping all radiation. They're more like a blanket with a bunch of holes in it. Remember that greenhouse gases aren't a single layer. There are lots of molecules floating around. When a molecule absorbs some radiation, it re-radiates it in all directions. Some of that radiation goes back down to the Earth, some goes up into space, and some gets absorbed by other molecules of greenhouse gas, which then re-radiate it in all directions, and so on. But how much will each greenhouse gas affect our climate? We can measure the global warming potential of a gas. A gas's global warming potential is the warming impact of 1 ton of that gas relative to 1 ton of carbon dioxide. Here we see the global warming potential of several common greenhouse gases. The global warming potential of carbon dioxide is, by definition, 1. 1 ton of CO2 causes the same amount of warming as 1 ton of CO2. The global warming potential of methane, by contrast, is 28. That means 1 ton of methane would cause 28 times as much global warming as 1 ton of carbon dioxide. Other gases have even higher global warming potentials. For example, HFC 134a, which is used in air conditioners, refrigerators, and compressed air cans to clean your keyboard, has a global warming potential of 1,300 times more than an equal amount of CO2. So why do we worry so much about carbon dioxide if other gases have global warming potentials many times higher? Because there's just so much more CO2 being added to our atmosphere. For example, since pre-industrial times, we've increased the concentration of methane in the atmosphere from about 1 part per million to just under 2 parts per million. But we've increased CO2 from about 280 parts per million to over 400 parts per million. So even though methane is a 28 times more powerful greenhouse gas, we have over 100 times more CO2, meaning CO2 is causing more total warming. When we add up the global warming potential and the amount of each gas, we see that the majority of our global warming has been due to CO2.